Okay, welcome to the highly anticipated ME773 final project. Uh, I'm Jack Pocketbeer. Let's get into it. So for this project, I'll be looking at the pasteurization of milk is the topic that I've chosen as a little bit of an introduction. Pasteurization is mainly used in the dairy and beverage industry for destroying harmful bacteria such as Salmonella, E. coli, and Listeria, which can cause foodborne illnesses, which we want to avoid. Pasteurization actually ties into the current research that I'm doing here at K-State. So my current research looks at utilizing nuclear microreactor process heat to power a bunch of different processes, and one of those processes is pasteurization. So I thought maybe looking a little bit deeper into some aspects of pasteurization and the elements of heat transfer going on would be valuable for my research. In this project, we'll be looking at two of the modules that we covered during the semester. So we covered conduction, convection, radiation, and multi-phase flow. The two that I've selected for this project will be conduction and convection. Also, here you can see an example of a plate heat pasteurizer, which is what I do most of kind of the modeling after in this project. So going into a little bit more detail about pasteurization for part one. Most commonly, pasteurization is done utilizing plate heat exchangers. Plate heat exchangers offer a lower cost, higher flexibility, higher thermal efficiency, and a greater ease of maintenance compared to other heat exchanger ways. There's two common techniques for pasteurization. You could either operate using batch pasteurization or continuous flow pasteurization. So for batch pasteurization, it's typically done in a large tank or vat where the milk will sit, and it takes a longer time to become pasteurized. So this operates at lower temperatures as well, longer time. And then for a continuous flow pasteurization, this is often done in an intermediate holding tube, and this is exposed to higher temperatures, but a shorter time. So there's different variations of pasteurization, but they typically vary from, off the top of my head, 50 to 150 Celsius being the extreme ranges that it can occur at. So the paper that I will be comparing some of my results to, and that gave me some of the ideas for this project, is called Milk Fouling Simulation in a Helical Triple Tube Heat Exchanger by Sahu et al. In 2005. So starting off part two, I considered a thermal resistance model. So the main issue that I thought was very interesting when considering pasteurization and was brought to my attention by Sahu et al. Was that fouling is a considerable thing to be considered within the pasteurization unit. So milk being a food-based product and containing protein, when these proteins are exposed to higher than normal temperatures, they can have protein reactions within the milk, and this can result in a fouling, which will result in a deposition layer on top of the heat transfer equipment. I wanted to observe how this thermal layer, or not thermal layer, this deposit layer affects heat transfer. But first of all, let's estimate this deposit layer thickness by using our thermal resistance model or a circuit analogy. So with the circuit analogy, you have your Q dot, which effectively acts as the current throughout the circuit, where your temperature difference would act as the voltage difference, and then resistance would be analogous to resistance itself. And then our resistance is labeled here. So referring to my sketch off to the right, I crudely drew it up, but this is what we're considering. We have two temperature differences, the temperature of the milk over here and the temperature of the steam going in opposite directions. This right here is the fouling layer, obviously not drawn to scale. And then the wall layer for the plate heat exchanger. This would be made out of stainless steel. They both have their respective lengths, delta, sub D, which I'm using as deposit thickness, and then length of the wall or thickness of the wall. So when determining the total resistance, you have to add them up. It's in series. You have nothing in parallel, so the current through them is all the same. But looking at this, we'll have two conductive resistances being from the two layers here, the fouling layer and the wall, and then we'll have two convective resistances from the convection going on in the milk and the convection going on in the steam. So yeah, let's go to the next slide. So we can consider an arbitrary case where I just let Q dot equal 3 kilowatts. And then I kind of had to build my own pasteurization unit. I think all of the values are reasonable. Mainly my idea was to get a general sense of the trends occurring in this system. So one of the major ones though were the convective heat transfer coefficients. So for H sub n, the heat transfer coefficient for the convective heat transfer coefficient for the milk, I estimated this using a correlation by Cedar and Tate, and then the rest of my values are considered here. I did kind of a ballpark value for the convective heat transfer for the steam, and then some of the other values I took from other literature which worked on pasteurization units. But with those in mind, we have enough information to solve equation 1 and equation 2 on the past slide. This gives us a deposit layer thickness of roughly 3.16 centimeters. And granted, I'm not a PhD in pasteurization, but this seemed reasonable to me. Now, after we're done with our circuit analogy, we can move on to part 3, which kind of switches gears, and we'll look at a derivation. Move my face out of the way. We'll once again consider the heat equation for transient conduction. We looked at this similar in project 1, but we'll go back to it. So we'll be assuming there's no volumetric generative term in our heat equation, heat generative term, and then we'll also be assuming that it's one-dimensional, an infinitely long cylinder, which I'll talk about that assumption, and then also axial symmetry. So that reduces our equation to the heat transfer coefficient, or the heat equation shown here. Our goal for this part 3 is we want to find the time required to heat a section of milk up to 63 degrees Celsius, which is the pasteurization temperature that I've chosen. To do this, we want to solve this ODE. So we'll need to non-dimensionalize our temperature, which is listed by theta, which is a function of the radius and time, and then consider some of our initial conditions and boundary conditions as shown here. Next slide. Continuing the derivation, we'll utilize the separation of variables, and this will give us a solution in the form of a summation, as shown here. This summation will come up again because we'll be using an approximation to make it much easier. And then lambda sub n is the characteristic value with n positive roots. Considering this lambda sub n and obtaining the transcendental equation, we can rearrange this to get this as a function of the BO number. Then we can introduce the Fourier number, which is the ratio of the rate of heat conduction to the rate of heat stored in a body. Know that gamma sub n is lambda n times R naught, and then plugging in our initial conditions and boundary conditions, we'll have enough to solve. But before we can finally solve, we have to consider, we'll use only the first term of the series. So this will be the one-term approximation. And this is kind of, we'll retroactively see if this assumption is appropriate when we calculate the Fourier number. So calculating the Fourier number from this, we'll have to plug in all the values that I have decided to use. So this T is our goal temperature, 63 degrees. T infinity would be our steam temperature, which I think was 125. Then our T initial would just be ambient milk temperature. I put as 20 degrees Celsius. and then we would solve for the Fourier number. To do this, we'd actually need to find the BO number first, which I found to be 5.49. We'll need this BO number as this is what's listed in table 5.1 to give us the constants C sub 1 and psi sub 1. I found those in the textbook. So plugging all those in, we arrive at a Fourier number of 0.235, which is greater than 0.2, which is the barrier for the one-term approximation being appropriate in this case. Then, now that we have our Fourier number, we can rearrange to solve for time using the definition of the Fourier number, which gets a time of 5.22 seconds to heat up a section of milk to the desired temperature. This may not be 100% realistic as the milk is flowing, but I was thinking almost to when we were working with the potato, and it's like maybe the milk at one section, this is how long it would take to cook up this volume of milk. So to change it up a little bit in part 3, I looked at some numerical results. So I was curious to see, so we established when this fouling layer thickness increases, the heat transfer efficiency will decrease. So I wanted to see how this decrease in heat transfer efficiency would affect the time to get up to our pasteurization temperature. So to do this, I manually decreased the BO number from our 5.49, which we started out with, and I decreased it all the way down to 1, which is directly representing our heat transfer efficiency becoming worse. So to do this, I would need new constants for each BO number. So I followed the table in Cropra to get these C and sub psi. So what we can see from these results is as the BO number decreases from roughly 5 to 1, the time increases. So this makes sense as we're getting decreased heat transfer efficiency, so we would expect a longer time to get to pasteurization temperature. Also, coming back to what I talked about earlier with the long cylinder assumption, this may be dubious. The infinitely long cylinder assumption is mainly for when our length over our radius of our cylinder is greater than 10. In my case, it was roughly 2.58. So it's not quite there, but I think still, even with that assumption being taken into consideration, the general trends back of the envelope is pointing in the correct direction. Going into part 4 for the final project, we'll be looking at simulation results. So to do this, let's use ANSYS thermal transient. So the question I proposed for my simulation is, how does the heat flux through our plate heat exchanger change as this deposit fouling layer thickness increases, delta sub D? This could be a case where you have maybe a negligent manufacturer where they're just like, let's not waste time cleaning. I don't think it's really that big a deal. This would be that case where they let it build up. So to do this, I created 2 surfaces similar to my thermal analogy, my thermal resistance network. One being the fouling layer and then the plate heat exchanger wall, again, made of stainless steel. So stainless steel they have in the thermal characteristics engineering data of ANSYS, but I had to put in the fouling layer thermal characteristics, which was the thermal conductivity, density, and I think the specific heat was the last one. Then after that, I developed the mesh geometry as well, and then considered the initial conditions and boundary conditions that I would set up. These were the milk and steam temperatures. So the steam temperature would be 125, the milk temperature being 63, and then set up my convective boundary conditions on each side. I was looking in ANSYS Fluent. I'm not sure, I'm still a rookie. I didn't know if there was a way to change your geometry and see how that affected your results in one simulation. So what I did is I created numerous workbenches, and for each one kept everything the same, all the initial conditions, boundary conditions the same, but changed and increased this fouling layer thickness in each geometry to see how that affected the heat transfer flux, the heat flux. So some of the results from doing that. So I noted as I increased this fouling layer thickness, a higher heat flux was needed to increase or to reach my goal pasteurization temperature of 63 degrees Celsius. That's depicted in this plot right here. So heat flux, watt per meter squared, and then, I don't know, I keep blinking on this, the fouling layer thickness in meters. Basically, what the underlying thing for this whole project is the fouling layer is a resistance to heat transfer, and it keeps being proven correctly. This is a little snippet from ANSYS where you can see the temperature gradient throughout. So it's kind of hard to see, but this right here is the stainless steel plate heat pasteurizer wall, and then the buildup of the fouling layer going to the right. So you can see the temperature is hot from the steam on this side, and then it decreases. Then for the final part of the presentation, we'll look at comparison from that initial paper that I considered. So milk fouling simulation and helical triple tube heat exchanger. Sahu et al. 2005. So some of the results that they found, or what they did, they discussed the problems with deposition of milk solids on heat transfer equipment, where it reduces heat transfer efficiency, as we've seen, increases the pressure drop, and necessitates frequent cleaning to keep up your efficiency of your pasteurization setup. They proposed fouling models that looked at flow patterns, temperature variations, and computational models, and then also looked at some of the impacts where they changed flow rates, shear stress, and temperature. Temperature being, I think what they said, the key indicator of fouling buildup. Higher temperature was much more fouling buildup compared to the low temperatures. So finally, looking at some of the results that I can directly compare to, they observed similar trends to me. So again, the moral of the story, increased fouling deposits will inhibit the heat transfer efficiency. So I thought their results were actually pretty interesting, and I thought they depicted it well. So their setup was a little bit different than mine. They used tubes rather than a plate heat exchanger, but still the story is the same. So over the length of their tubes, roughly 2.3 meters, they plotted the inlet and the outlet temperatures and how they evolved going through that length, and then looked at different temperatures, or not temperatures, times of operation of their pasteurization system. So initially at a time 0, that's this top line, they all start at the same temperature. And when no fouling has time to build up at all, they are reaching an outlet temperature of about 140. So this would be the best operation for them. But if they neglect cleaning and let it go to all the way hour 40, hour 45, yeah, I don't know why I would like hour 45, then you can see that their temperature goes significantly lower. Actually, this one's not even depicted on there. So it'd be 90 minutes. They'd only get like 118 compared to their 140 right here. So it again just shows how this fouling is inhibiting heat transfer coefficient, the heat transfer through the system, increasing the pressure drop, a myriad of undesirable effects. So to finish off, here's some of the references that I looked at, and then Fian. So thank you for listening and following along. I had a lot of fun this semester. I learned a lot, and I think it was a very good class. That's it. So like, subscribe, hit that bell. That's the end.